everyone, welcome back. So today is in my small town home. It's also beautiful today. The weather is nice, not raining anymore. So I'm happy to show you what the lesson today looked like. Okay, so today I would have a new lesson to all of you, which is we call a logistic function. Now, some of you may be familiar with this already if you take calculus or, in your college or whatever you learn in the high school math 12. Some of you may be familiar with it already, and some of you may not. Now, in my course, I assume that you haven't learned this topic. And I'm going to start from there, right? So let me show you what the logistic function means. On the board, I have two functions, right? One is the exponential function, and everybody already know about that. On the right-hand side, I have a curve, very much like this one. However, when it go to the two knuckle here, when I put the line here, I show you this part look like this part, right? And then eventually this one, the difference is this one eventually curve down, decline, and then eventually no longer roll up like this anymore, and eventually curve down and hit the line here. So that is the difference between the two functions, shape, right? The shape of the function. And from our observation, we see this very much the same. The exponential function rho show that this function keep growing, and therefore we have a formula P respect to time equals CE to the KT. Everybody know that before, right? Now, what is the formula for this one? We don't know. I will talk about that, but not yet. Now, I just want you to analyze the shape of these two functions. So this function look very much the same up to here, right? But then to this part, it curves and eventually curve down, and the slope of it becomes 0. Now, when this function draw up to this horizontal line, asymptote, we call it asymptote, it no longer be able to draw anymore. It just never hit this line below this line, right? Beyond this line, but never hit it. And the slope like very flattened, it's like m equals 0. It means the rowing rate is no longer row anymore, right? And that's why we're talking about two different things in here. And I like to put in the concept, right? So in our life, we have something or certain species, certain cultural bacteria, certain population grow in a unlimited resources. And why? Because they get away from, they have immunity from disease, they have a sufficient food source and climate good and everything good, and they don't have a predator to eat them, right? So that we call a natural growth. Then that is the exponential function. Now, on the other hand, in our life, in our real life, we also have a certain population, or like our money we put into the investment stock market, and it keep growing, right, with a very high rate. Unfortunately, if the stock market crash, we lost money, it no longer grow, our money no longer grow, or in a certain environment, the certain species were being eaten by a predator, or like their birth rate is very low compared with their death rate. So eventually it dying out and it no longer grows anymore. So that is about logistic function, the row with the limited resource. The other one is the row with unlimited resource. The other one is the row with limited, right? And the limited resource here, we call a K letter, we denote by the K letter. And we call it as a carrying on capacity. A certain limit capacity stop the row. You only can row up to 1,000 or 800. population. No more than that, right? So we call that letter K is the K letter carrying on capacity. And the formula to describe the logistic function is, this is PT, so this is the same like PT. It means population respect to time equal a certain R rate, right? Let's say your row rate is 0.066%, and you multiply with the P population, right? So the rate of change of a population respect to time equal the rate of row multiplied with that population. So this equation makes perfect sense. However, because we have limited row, right? And this we call a logistic. So we have to have another multiply with something like this. And this formula K, we call a carrying on capacity. Carrying on capacity. And if you make observation with this and this, you see it too. Because let's say your forest environment only can contain the row up to 1,000 species. And this K is equal to 1,000 species. Let's say if this K equal P, then what happened? The K here equal P, then P divided by K is what is the same number divided by same number, it equal 1. And 1 minus 1, this root will become 0. If K equal P, right? If these two numbers equal. So that's why the slope of change of it, when it row rate hit this line, the slope becomes 0. So as t went by, if you notice the function, if t getting closer and closer to 0, then this behavior look like a rowing. It will row very fast at the beginning as well, right? Just like exponential row. But if the t here getting big to infinity, if t here get to infinity, then this function behave like cupping flattened out, right? Like this. So it means as t went by, the population increase, instead of increasing, keep increasing, it stop at some point, right? If it hit the same P here equal the K capacity here. So that makes sense, right? So that's why the mathematician developed this formula for us to follow. So now after this, we also learn, therefore, the formula of this differential equation will be equal P times T, P of T, the function of population respect to T, equal K divided by 1, adding with C, e to the minus RT, or KT. This is a big K, the small k. Now, because we use both the same K, so I don't like to use the same letter, so I change the K here, become an R, but which is the same, right? So I just change R because we have a big K already, and I don't want to be, confused with that K. So I just change the letter, become R, okay? So that is the formula. Using this formula, be able to solve something like this. So in our live application, you will see something like this. 200 fish were put into the lake, whose carrying capacity for that species is estimated 10,000. The numbers of fish quadruples in the first year. Find a formula relating to P, the number of fish in the lake, with T years. Since the fish were introduced, how many years it will take to have 5,000 fish in the lake? So I'm going to leave this application after our lesson, right? In this lesson, I just want to explain to you about the logistic function, analyze the shape of it, and show you how we derive the formula. Now, you will question me, how come this formula become this formula? I know that, right? So that's why I want to show you this. Okay, so I'm going to show you, I'm going to prove to you this one equal this one, right? Now, let me copy this formula again. And this time, instead of put p with respect to t, I can put like dp, derivative of p over dt on the left-hand side, equal a certain rate multiplied with that population p times with r minus p over k. Okay. Now I'm going to do something inside the bracket. So I'm going to make a common denominator. So this will become dp over dt equal r times p. And I'm going to put 1 underneath. So this time k, top time k. So this becomes k minus p, all of them over k. So this is the differential equation. If we solve this differential equation, eventually we'll get up to here. Okay, so how do we solve that? Remember, I told you the way we solve differential equation, first step, separate the variable. Like remember before we do something like this, dy over dt equal ky, right? And then we put the k underneath and we put the k dt up here, right? That's how we first learn. Now we do the same for this, right? First step, separate variable. And by this, in the meanwhile, I will do cross multiply as well. Cross multiply. Cross multiply, it means I'm going to bring whatever on the top level, right, will go down, and whatever on the down level will go up. That's what we call a cross multiply, right? So now I'm going to bring the k up here, and I hope you still can see it. Yes. So I'm going to bring the k up here, so we have k dp. And down here, we have a bunch of them, except the r here. I'm going to leave it on the right-hand side, right? So the p will go down, time with k minus p will go down. Okay, and I'm going to put the dp in the middle as well, like that. That's okay as well, right? And the dt down here, I'm going to kick up here as well, so r times dt. So that's how I do separate variable and cross multiply using cross multiply at the same time. Okay. Now, next step, I'm going to integrate both sides. But before I integrate them, I'm going to do like something like separation. So the first equation, let me copy it down again. I'm going to focus on the left, right? The right-hand side, not too much, so I'm going to focus on the left here. I'm going to separate this fraction, become two fraction. And I'm going to write this become 1 over p plus 1 over k minus p. And of course, all of them will be dp equal r dt. Now you might ask me why. Why this become this? It doesn't make sense, right? If you learn about the partial derivative, you understand why we can split like that. However, because we haven't learned about partial derivative, so I'm not going to bother to use that method to show you. Instead, I will show you the very basic elementary concept. to prove this is true, right? And it's true. Now, why this is true, we can check, right? Let's say we check, we suspicious about this. We're going to check, okay? If I do common denominator this, right? Then the first fraction, I'm going to time with k minus p. And down here is p times with k minus p. Adding with the second fraction, I'm going to time with p on top. And down here, I have to time with p at the bottom, right? That's true. If you add these two fractions, and you want to come up with the common denominator p times k minus p like this. These two brackets like this, right? So you want to make common denominator. Now, eventually, you can cancel this with that. And you also can cancel this with that. And you get back to 1 over p at 1 over k minus p. And that is true. Now, obviously, you see it right here, right? But I'm going to talk to you. I give you a hint about elementary basic. Let's say I don't know a number on top here. And I have a fraction on top. I don't know what number is that. Down here, I have a number. Let p equal 6. And let k minus p as the one number equal 2. Now, I know that I can split this fraction, become 1 over 6, adding with 1 over 2. Now, why it like that? Because I know that if I add this fraction, I want to have a common denominator 6 times 2, 6 times 2. So this fraction have to time with 2. On the top, have to time with 2. So this will be 6 times 2 on top time with 2, adding with this fraction, have to time with 6. And down here, have to time with 6 to make common denominator to become, we can join them like this. 6 times 2 equal 12, right? And the top here, let's say if we don't cancel it, it will become 2 on the left, adding with 6 on the right. And that will become 2 as 6 equal 8. So we know the top have to be number 8. And that is true, right? So this is just the manipulation of the common denominator in elementary ideas. We can put in here and separate the fraction like that without doing the partial derivative. Eventually we will, because if we put in partial derivative, it's derived from the same idea, except that in more formal and with more complex number. And in math, we tend to do informally so that we can deal with hard number, square root, power, whatever it is. Because if we follow the pattern, follow the formula, it's going to be true. And we can manipulate with lots of different number and size and things, right? It's less complicated. Otherwise, it will be complicated. And that's why we have to learn partial derivative later on. But at this point, in this logistic equation, I'm not going to talk about that, right? So you see this, what I mean, right? So we now accept the fact that this equal this for now, okay? It should do common denominator, you see that, right? Okay, so now, after this, I'm going to integrate both sides, okay? So I'm going to integrate 1 over p, and I'll put dp here, adding with integrate 1 over k minus p dp equal integrate r dt. So integration of 1 over p equal ln p, absolute value, adding with ln k minus p, absolute value, equal r times with t, adding with c, constant number, we don't know, right? So now at this point, I need to change this positive become negative. But how do I change it? Because in math, you never can change something without compensation for it, right? So if you remember the math 12 log of A to the 1 over x. If you change this become negative, then you have to twist this fraction 1 over x become minus log of A x over 1, or it's just x, like that. That is the formula you learn from logarithmic rule in math 12, right? So we're going to apply this formula in here, okay? So this will become ln of p, adding with ln of, and instead of adding, I change it minus, right? Minus ln, instead of k minus p, it will be 1 of k minus p, right? We have to inverse the fraction, right? So this k over p over 1 become 1 over k minus p. So this we just apply the logarithmic rule like here. And on the right hand side, we still have rt plus c. Now I'm going to need some more room in here. So I'm going to erase this. So we have ln p minus. Now in logarithmic, if you have a subtraction product, a subtraction and they both ln the same base, ln e, right? Then you can join them together. That's the rule in log as well. So now I'm going to join them together. So I have ln p, subtract become divide, and that is 1 over k minus p. And that equals rt plus c. Now, because we have a fraction divide a fraction, right? I can do whatever inside here, outside still long, but inside I can twist it, become k minus p on the top over p at the bottom, right? That's how you divide fraction, right? The inverse fraction equal rt plus c, nothing change. So now at this point, I'm going to raise the e both sides. Okay, I'm going to raise the e base both sides. And when I raise e to the ln star equals star, right? That's the formula in the log too. And that is true because e to the ln star equals star, that's the formula. So if you have e to the ln 4, it will be equal 4. If you have e to the ln 5, it will be equal 5. That is always true, okay? And if you want, you can use a calculator and figure out that as well, okay? Now, we're going to raise like that. So this log will be canceled. However, I'm going to change this a little bit. So I'm going to put a negative here. Let me see. Okay, so we are doing up to here. Now, I am going to do something about this. At this point, let me put in the negative this way, and therefore, on this side, that will be negative. Everything here will be negative as well, right? Okay. Now, why I do like that? Let's see. So now, I'm going to bring the answer for this down. Ln e to the star equals star. So if you have ln e, I remember this formula, right? Let's see, my Chinese teacher taught me. Ln e to the star equals star. Like his was my high school teacher, my Chinese teacher. Ln e star is the star. So it means if you have ln e of 4 equal 4 and ln e of 5 equal 5. And that's true, right? It always like that. You can use a calculator to validate that as well. Okay, so now ln e to the star equals star. So it means this is the star, and we have a negative, so it becomes negative k minus p over p equal minus r, no, equal minus e minus rt time with e minus c. But e minus c is just the same like a constant c number. So we're going to bring it up here. We will leave like this, right? Now at this point, I'm going to change this become positive, and I'm allowed to change this positive as well, okay? So whatever I do to the left, the same like I do to the right. There's nothing wrong with that, right? Okay. And I don't have to put the positive actually. So now, what do I do next? I'm going to separate this equation. To separate this will become k divided by p minus p divided by p equals c e to the minus rt. And now this cancel out. We have k over p minus 1 equals c e to the minus rt. So now I'm going to bring the 1 over. So I have k over p equal c e to the minus rt plus 1 because I bring it over, right? So now there's just one more step. You will see it. I have to erase this. So at this point, I'm going to bring that up here for you to see, right? So we have kp equal, I'm going to put 1 in front instead. Same thing. Now I'm going to twist, reverse the fraction. Now when I inverse the fraction, I inverse both sides, right? I put 1 underneath and I inverse both sides. So my function now will become so okay, let me see. So before I do that, okay, what do I have? Yeah, I have kp. Yeah, so when I inverse the fraction, I have p on the top and I have k at the bottom. And this also inverse 1 on top, 1 plus c e to the minus rt. Now at this point, if I bring this up to here, right? Yeah, I can do that as well. So I can divide, become multiply. When I kick it up, right? It's gone. So now, what do I have? Now, after I do this, I can join this in here, and my function is p equal k over 1 plus c e to the minus rt. And we can know that this function actually is a population rho p respect to time equal this. And this is a formula of logistic equation that allow you to use this formula to calculate any problem like this easily. Okay, so in this video, it's a long video. I just want to show you the proof of the formula. But then after that, once we already know where it's come from and how it works, we accept this. It's become easy. We can use this and apply to our word problem and solve for it. So that will come to the next video. And so I will have to stop our video right now. And this topic will continue for a while before I get into another topic. So I'm going to go through with you maybe another 2 video involve the logistic solving equation, maybe 1 or 2, and then after that I will get into another topic for our calculus course, the second course. So you will see a lot of interesting topic coming up in our my online teaching, and I hope you enjoy and have a good day, have fun today. It's a beautiful weather. So thanks for watching. Bye for now. Stay tuned for the next video.